your session.
That's okay.
So another professor will replace him, Professor Bùi Trọng Kiên from Institute of Mathematics, Vietnam. He will
Thank you.
chair your session. Okay. Thank you very much. I don't know if Professor Bùi Trọng Kiên he here with us.
Are you in France or in Hanoi?
Actually, I'm in France.
It's quite late now, isn't it?
Now it's quite early in the morning.
Yeah.
But it will be it's very happy to be here to hear your talk.
Glad to see you in a virtual mode. Hopefully to see you face to face sometime in the not too far distance future.
Yeah. I hope it's so. Okay, so now the chair is here. I will. I don't know if he.
Hello, Professor Zhu.
Hello, Dr. David.
Come from Institute of Mathematics. So I chair the section now. The next speaker is distinguished Professor Zhu. He comes from Royal Melbourne Institute of Technology, Australia. Professor Zhu is an Associate Deputy Vice Chancellor and Vice Chancellor Professional Fellow at Royal Melbourne Institute of Technology. He was President of IEEE's Industrial Electronic Society for 2018 and 2019. His main research is about control system, intelligent and complex system, energy system. And today, we talk about discontinuous control technology, challenges and opportunity. So please present the talk.
Yeah, thank you, Professor Trump. Hello to everyone. It's glad to be here. Because of the COVID, of course, we can't see face to face. But I hope that in not too far distance future we will be able to see each other. I have been in Hanoi, no, not Hanoi. I have been in Ho Chi Minh City for a few times, but I have never been in Hanoi. So hopefully next time we'll see Hanoi. You know, as you probably know, that RMIT has a campus in Vietnam, probably the only foreign university allowed to open the campus. So I'm sure that you're not too unfamiliar with the name. So hopefully we will see each other another time. So today what I'm going to talk about is really just from my many years of research experience looking at this continuous control. So more broadly, as Professor Chuang was from Institute of Mathematics, more broadly it's about differential equations with the right-hand side discontinuity. So that's kind of this. So basically just share with you some of my experience across various aspects of this continuous control and look at some main methodologies. And in particular, after at the end of the talk, we will speculate what are the challenges in the future. I think this will be very good for researchers and also in particular for the young postgraduate students. Okay, so let me just start sharing my slides. I hope you see it's okay. Is that okay? Is that slide okay? You can see it?
Yeah, I see it very well.
Okay. So what I'm going, this is actually going to be quite, I would say, it's not going to be mathematical intensive. As an engineer myself, we try to use the physical understanding to interpret it, to understand all these issues. So they shouldn't be very mathematical, but of course we do have some. So you have to have some mathematics to show the properties. But I hope that's sort of very minimal. So firstly, what are we going to? Is that the discontinuous control. So as I mentioned before, the discontinuous control basically are the ordinary differential equations with right-hand side discontinuity. Here, this is a typical, if anybody have learned control theory or control system courses in the undergraduate or postgraduate, you would know that this is a typical way we describe any practical industrial system. So you have it described by ordinary differential equations. So most industry processes can be described by ordinary differential equations, but there are some, of course. For example, those chemical engineering, chemical processing plant, they are described by the partial differential equations, but then there's another branch of study of that, but that's become much harder. So we only focus on the mainstream of control theory. So this is actually a typical, differential equations with right-hand side. You can see on the right-hand side there's U, which is basically it's a control. Control you can design whatever you like to try to achieve particular goals. So we all know that in the theory of differential equations, that the function has to meet the Lipschitz conditions, right? So this is then you have this kind of existence uniqueness of the solutions. However, if you have a discontinuous control and that conditions may not met, so that's the what we know so far. So if you look at this, I'm assuming that audience here, many of you are either engineers or computer scientists or mathematicians, applied mathematicians. So the discontinuous control, you can see it everywhere, right? You can see from the very basic control for the induction motors or the inverter converter, or air conditioner. What you have is you only have a few switches. In a switch, we know that it's usually 0 and 1, 0 and 1. So basically, you have a switching system, right? And you take depends on situation. If you look at the right hand side, you take whichever control vector. You only have a limited number to choose. There's no other choice. So you just pick one. But you can see that you have for example, here you have three switches. Three switches. So you basically have 8 possible choices to make. So and then this becomes a very typical switching system. If anybody dealt with, for example, fuzzy control, is another you can consider as a discontinuous system, right? It depends on the conditions. You take different actions. So that action is actually causing the system right hand side is kind of discontinuity. Time optimal is another one. Time optimal. This is actually time optimal control is usually switching control, which is quite understandable because we know that the most effective control is the switching. For example, when you drive the car, you want to maintain a particular, let's say, 60 km/h speed, and if you the accurate the closer to the 60 km, the faster you have to switch your foot, right? On, off, on, off. So this is a very, so it's quite consistent with our experience. You can also have like impulsive control. This is a bit rare. Probably most of the application might be in the space because you only have just give an impulse to the control, just push it. But those usually in the space because you don't have much friction in the air, so that can be done. But that's you can consider it's another type of switching control. Event trig is also a very recent one. So event trig means that normally when we say we design a control system, we require the feedback of the condition of the system to the is in real time means the information will be supplied to the system, to the controller in real time, all the time. But in fact, there's no need to do that. So this is the more inspired by the telecommunication. In telecommunication, you just you only carry the information. The message, the signal is actually in the pack. So you only transfer this in the pack, and you don't transfer the information all the time. So that makes lots of sense, because then if I have a remote control, for example, control over the internet, and I don't need to transmit control signal every second or every millisecond, even faster. The only thing I need to do is I just need to find the condition that when it is needed, I transmit information. So in that way, you can see it will save lots of bandwidth, in particular in the large scale network control. Of course, this is a typical control signal. You have controllers. You just choose, depends on the situation, you choose whichever you like to achieve what you want to achieve. So sliding mode is the one, if somebody has been doing switching or sliding control, you probably know I've been doing that for many years. This is basically still using the switching, changing control force to basically, the only difference is that you design sort of switching manifold or surfaces which represent the system properties, and then you just force the trajectory into this surfaces and stay in it, then the whole thing, and then you basically have what you want. But of course, this is a very, as I mentioned before, switching control is very sort of I would say brutal control, means pretty strong. Okay. So usually the theory of this control, because we're going to touch on sliding mode a little later on. So usually the benefit of using this kind of force is that when you realize the control, for example here, you design this manifold representing what you expect, and you can derive control. So eventually the control system itself, to control the system itself, is have this kind of motion, which you can see is kind of independent of the disturbance. If this is disturbance, you can see that actually the system driving, the dynamic driving the system has nothing to do with the disturbance. So that's actually the benefit of this kind of switching control. That's one of the reasons why there's so many people using that. Okay, so let's just look at the discontinuous. What's the properties about this, using the discontinuous control? So one of the things to demonstrate that, let's just look at some very simple example to show that the benefit of switching. We know that when you do the switching, you violate the Lipschitz condition. What I mean, that means all the theories we have for the ordinary differential equations cannot be directly used unless you have to modify it, accommodate this kind of switching. So here's just to take a very simple example. You can see there's two switching, two system dynamics, and the only one way you can do, you only changing, depends on situations, you only changing this parameter between these two, right? So what you get is like this, right? If I set particular parameters, on one I choose one of them. So this is actually the, let me see, where is it? So this is actually, you can see that for the red, if I choose the red one, so this is actually the phase plan trajectory, how the system will evolve. And if I choose another one, so this is actually, it becomes a parabolic stable motion. So, but the beauty of that is if you're switching, you can stabilize the system. Right. So what that means, that it's physically pretty easy to understand, is you just piece these trajectories together. For example, if I want the system converge to here, what I need to do, if it's in this phase, I choose the blue controller. Right? Blue controller means that actually you can see it's actually closer to the target. And then when I'm into the fourth phase, I choose the red one. So you can see it converge. So just by doing that, you can just choose the controller, eventually stabilize the system, right? So basically, even these two systems, one is sort of stable, this is I should use this example. So basically, by doing this, you created this kind of a very stable system. On the other hand, if you have two stable systems, this is the example, two stable systems, by switching, piecing together the trajectory, you can create an unstable system, right? So I think that's, but this is actually usually, at first it might appear to be a little bit hard to understand, but it is, but if you think further, it's not, because the stability does not mean the trajectory uh, at every step going towards the equilibrium point. Does not mean that. It means overall, it will going towards equilibrium. So sometimes it grows, sometimes it shrinks, but it's a shrink more than growth. That will eventually result in the system trajectory getting into this equilibrium point. So that's actually an example. So but there are some kind of relations between this continuous system. They are sort of not isolated. I just use this as a very typical example. Let's just look at this double integrator, and then that's just using very simple control. So basically, what you have this kind of you can see if I build the Lyapunov function, which is energy function, the energy is zero. The change of energy is zero. What that means is that means it is stable, but it's not asymptotic. It does not converge to the equilibrium point. So basically, what you do is you buy a piecing together of the trajectory. You can create this stable system. For example, here I have two. One is k1 is greater than 0, less than 1, or another one. So you have this kind of trajectories. You have this kind of phase current project. What you do is if you create this kind of stability theory, you can create this switching condition. Eventually, you just pick up the pieces and connect together. The system is stable. So this is a kind of intuitive physical interpretation, but mathematically you can prove it. So this is the sort of mathematics eventually you prove it. It is the case. And also, if you go a bit further, you can see that it's actually converged. But in fact, close to the zero, you can see there's actually motion here. It's become attracted, so everything will sucked into it. So this is we usually call this is actually we usually call sort of a sliding mode, because that line, the red line, become invariant, right? It's just everything coming into it will not escape. So this is just so if we classify how do we see this continuous control? We talk about different discontinuous control. How do we see them? So one way you can see them is there's two ways you can see them. One way is that you can see that there's a dynamic where the discontinuous occurs is actually between different dynamics, right? You choose different feedback. You have different equations, so you're actually switching between different dynamics. So another way is actually it's different. It's the disruptive bring one state to another. Like impulsive is actually inject enormous energy at just a very short time, and then they move the state from one to another very, very quickly, sharply. So if you talk about the control between different dynamics, your trajectory will be continuous, but your control may not be. The discontinuity still exists, but if you look at that's a different equation where you integrate it, it is continuous. But in this type of control system, it is not discontinuous because the state is jumping from one plate to another. Okay, so there's a particular thing about this switching is usually we usually call the Zeno phenomenon. The Zeno phenomenon is actually can be interpreted like this, right? You have bouncing balls. You put the ball there. You can see ball just bouncing on this hard surface, but it's actually damping. Gradually it's actually stabilized. So what it actually says is that it says there's actually two behaviors, right? One behavior is that, as I was saying, when you use the kind of a switching. So this is actually kind of switching. You have a free fall. As you can see, free fall is a control, some kind of control, and then the surface has a resistance, so you have another control pushing it back. So you have this bouncing between, but there's two phenomena. One is you bouncing so fast, and the distance between the one to another becomes smaller. So this is we usually call the jittering on the sliding on the switching control. And another one is general Zeno, means that eventually they actually have an interval, means the time is not they are not closer to each other switching time. Rather, there is actually a lower bound. So this is actually usually the Zeno phenomena we have to be aware of. Okay. So the question is, when you say the discontinuous switching, right? Then one thing you have to deal with is this kind of frequency, how fast you switch, right? So there's three. I usually classify as the three. There's a low frequency. Many of the existing methods can be used. Low switching means that you don't switch very fast. You could switch in time or in space. As I mentioned before, in time means that you have discontinuity and then you switch. Yeah. But if you're not switching fast enough, for example, you take quite a bit of time to take the next switching. So because if you're not switching, that system is a smooth system, right? It's kind of continuous smooth system. So basically all the existing theory applies. You can use the control theory or this modern control theory to study it. But the trouble is that when you have high switching, very fast switching, and then you just realize that this kind of you end up this has become non-smooth system, and then you realize that all the theory we learned so far, meeting the Lipschitz condition, do not apply anymore, right? So we will touch on later. The thing is in between, and it's not fast and not slow. So what are you going to do? I mean, that's actually a very challenging task. So one thing I think I would like to draw the attention of this continuous control or switching control. They are very sort of peculiar in the way that I use discontinuous discretization as a typical example. The peculiar in the way is this kind of fast, low, and high is relative, right? We will give an example later on. Another thing I want to talk about, because all this control will be digitized, so that's causing more problem, because when you digitize it, you actually introduce time delay. It means the control is supposed to be act. It cannot act because you digitally implement the control, so you have to wait until the next moment. So the challenge of that is it causing a lot of problems. So here is another very simple example. You can see that second order system, just like we had before, you basically eventually you have this system switching between plus and minus. And we know this is a similar situation, is that you have two dynamic systems. They have their own phase plane trajectories. So what you do is you combine them, you basically create this kind of stable motion. So basically, if I using this line as the desired dynamics, which is actually x1 plus x2 equals 0. So x1 plus x2 equals 0 is basically x dot equal to minus x1. So we know that it has eigenvalue minus 1, so it's a asymptotic stable. Just an example. So basically, if the trajectory is here, you take this control. If trajectory cross the line, you take this control and the control system. So basically what you do is that you come from here, it will arrive here, and when they cross the line, you take this control, they push it back, so eventually you create this kind of a stable system, right? A stable asymptotic line. So this is actually designed. This is we design, and we want to realize it. So this is very typical. But the problem is if you digitize it, it means you sample it, control sample, because it causes time delay. So what you see is that it looks initially quite alright, but later on you found it's actually suddenly it converts something, suddenly they just move away. So one of the problems is that it's here, right? When you start from here, you arrive here. But the problem is when you digitize it, you always have this time interval, right? Then if the time interval is too big, you jump into below this asymptote. You can see that there's asymptote here, right? When you jump below asymptote, trajectory moves away and never go back. So that's the reason you're causing this, kind of divergence. If you do a bit further, then you realize it's causing this kind of quite chaotic. It's very sensitive initial condition. You can see that it's like this. So what we did eventually, we realized that there's actually up limit. So up limit is you can choose parameter. Eventually, you can design the up limit. So up limit means that sampling period cannot be larger than this. If it's larger than this, this sliding motion cannot be guaranteed, right? So this is actually usually, at first instance, it looks like contrary to what we usually understood. If you simulate the differential equations, you say if the sampling period is small enough, then whatever you observe is actually the behavior of the continuous time system before digitization. But if it's a discontinuous control, it is not necessarily the case. Here, you can see that this is 10 to the -3. It's all millisecond level. But you may say that's still big enough. I can tell you if I choose another set of parameters, I can choose to whatever small you want to have. 10 to the -8, I can choose the parameter. So what that means, that means this kind of, when you're dealing with this continuous control, you got to be very careful that if you're not choosing small enough, the small is relative to the parameter, not relative to what we believe is relative. You might have a completely unstable system. But fortunately, this situation usually will not occur because usually the physical system parameter have a very big margin in terms of stability. It wouldn't cause the problem. But I'm just showing you mathematically, it does have this kind of issue. Another thing is the rich behavior of switching, right? If you digitize it, what do you realize? This is another very simple system. You just have a band switching. You can see that, as we say, you swing, eventually stabilize the system into the equilibrium point. But if you digitize it, then you can see that it's initially still looks like what we want. But when the sampling period becomes bigger and bigger, you can see it's kind of become isolating. Eventually, it looks like a limited cycle, right? So if you examine it further, so this is actually, we actually examined further, is that for the given the sampling period and the parameters from different initial state, you actually converge to different period. For example, you may converge to a period 2, that's 2, and 4, 6, 8, 10. You may converge all this. So there's very rich behavior when you're dealing with the discontinuous control. In particular, when you digitize it, you have all this rich behavior. So sometimes, initially when we start doing what we thought that's because of digitization, the noises. But in fact, it wasn't the noises, it is the system property. So if you see in the future when you do the implementation of discontinuous control, and you found that there is if you draw the diagram, you found that around the equilibrium point there is a black dot there. Just go into it to see what happened. It may not be because of noises. It might be because of this, this kind of digitization issue. You're causing this kind of, system not converge, rather isolating around the equilibrium point. Okay. You can see that we found, many possibilities for that parameter. You can see for the parameter there are so many periods. But you can see one of the good things you can see is that for the period 2, the area you start. What that means, when you start the area, you end up with period 2. So what we do is we just draw in the map, draw which area, basically using intensive simulation. You start from there, whether they converge to 2 or 4 or 6 or 8. But you can see that in most of cases, which is you can see the area is quite bigger. They are period 2, 4, 6, 8. But if you talk about a higher period, and their sort of area becomes sort of smaller. It becomes smaller. So this is to show you the even so we have a very rich behavior, but regular behavior appears to be you're more likely to see the usual behavior. Okay, so theory. So what was the current theory dealing with all this type of thing, right? So one way of dealing with, as I mentioned before, if you're not switching fast enough, you just visualize, just imagine what you can do is if there's no switching and there's a long enough time, then you can use existing theory, linear control theory, or other Lyapunov theory, design, the pole placement theory to design, and you hope that when you piece them together, the system still maintains. So we know that already from counter example that even two systems are stable system. Combining together does not mean it's still stable. I can actually create an unstable system, right? But that's actually the thing. So what you have to do is that you basically, for each switching control, you design the diagonal function. This is one of the ways we do. The only way you have to be careful is that uh, uh, that you have to linking them together means that you have to. The theorem basically say that you cannot switch too fast. You basically have to wait until minimum time so that these two, the trajectory actually maintain towards the critical point rather growing. So basically, this theory said if you for different switching, if you have two switching control for control one, control two, I have this diagonal theory. I design controllers, but there's the only way I can guarantee the system, the global stability, is that I have to wait until a particular time to switch to another control. Right, it means then this control design is becoming effective. So this is quite understandable. There's lots of theory here. There's a multiple Lyapunov theory and all sort of thing is actually along this line. So this is very sort of fundamental theory. So this is if you're not switching fast, fast, you can do this theory. Another way is that if you switch very fast, right? In particular, in the open loop control, switching very fast. But when you're switching very fast, we know that the existence uniqueness condition are not met. So there's a engineering kind of engineering oriented approach is that if it's switching too fast, and if it's it is fast. And it is periodic. I won't say fast. It's periodic. It could be fast, but it could be periodic. What you need to do is because when you have a differential equation with time here, we know that it's very hard to get solutions, right? So what you need to do is because we know that this is periodic. So the way you can do is you just integrate it, right? Average it basically. Integrate it, average it. And then you study these simplified linear equation, differential equations. And this is much easier because you can see this is an autonomous system, there's no time involved. So it's easier to solve. So basically the theory said that if, the initial conditions, you can see that if the initial conditions, they're not too far away for the same. So eventually they will converge. You can use this simplified average system to study this much more complex differential equation. So this is a sort of average theory. It's being widely used in engineering, in particular in power system. We know that when you have AC, it has a sort of base frequency carrying all the energies. So that's what you do is for that differential equations, you integrate it. So then you're dealing with time invariant linear system is much easier to study. And then this theory will tell you that whatever you get from this time invariant average time invariant theory, the stability would mean that the original system more likely to be stable. But of course, we know that it just to give you an indication. Does not give you 100% guarantee, right? That's the average theory. So another control is as I mentioned before, is sort of very fast. As I mentioned before, if I want to maintain 60 kilometers per hour precisely, and in theory, my foot has to switch in infinite time, right? When it's above 60, I decelerate, and when it's below 60 accelerated. My foot has to be switched so fast to maintain that accuracy. So basically, in that kind of differential equations, you can't solve it, right? So Philip's theory come along. Basically, what it says is that it just say that you don't have to worry about it. What you need to do is that if it's a switching between these two control vectors, you just choose any one in between. and then you use it as an approximation of the solutions, right? So that has become very popular in the engineering design, because that's just give us some guideline is how to dealing with this kind of very high switching. Average theory can be applied, it's related to as well. So average method is basically when you have this kind of a time period, but this is not time period, you can consider this a state. So the periodic, you can, I mean, basically physical theory is kind of an average theory in that sense, in the space sense. The challenge we have is, as we mentioned before, when we're dealing with not so fast low switching control system, we know that the piecewise level theory tells us that we have to wait minimum time of that so that all my control analysis stack up, means it tells me the system is stable. And here, basically say I have to switch so fast, then I can basically describe the system in an average way. But the question is what's in between. This has become actually the, I would say, is an outstanding problem. Still hasn't been solved at the present time. So anybody has a very strong mathematical background, you might just look at that to see what's in between. How do you dealing with the transition from very fast to very slow? So what's happening in between? We already demonstrated that there are examples of chaotic behavior, how to understand it. So that's become sort of a very challenging task. So one thing I want to talk about is just very quickly, briefly talk about is the terminal sliding mode, which is the theory we created over last established over last 20 years and has been sort of widely used. So this is another particular way is designing the control system. So what the reason we're doing that is that this is the conventional control design. This you can see this is a smooth, right? This is and it is so what do you do? Then we have asymptotic stability. Asymptotic stability is like this, right? You have this differential equations which has eigenvalues, and then when you solve that, you can see that the distance between this x and y will converge together. But just remember, they never met together, right? They never met, right? Because if they met, then they destroy this uniqueness, because you cannot have two solutions eventually arrive at the same place. So that's the problem of this is easy to understand, to analyze, but there's an issue but in the you may wonder why, what does it matter? It does really matter in particular in the engineering system, for example, robotic system. In high precision control, you want to have a very high precision of reaching the target. So one way you have to do is, if I use this theory, I have to increase the control force, so push it as close as it can be. There's another way is, then I don't have to use a very strong control force, because a strong control force means more investment into the equipment, right? It's a much bigger, powerful controller, energy. We don't have to do that. We use this, let's say using this type of thing, can use this fraction of, there's a fraction of power. This is where usually, undergraduate we know clearly, we know that eventually you actually found a particular time when they exactly converge together. Of course, it violated the Lipschitz condition, but it brings a lot of benefit. One of the benefits it brings is that they actually, when you're closer to the target, the control force is stronger. So eventually reaching final time. So with that kind of idea, we quite a number of years ago, we sort of introduced this type of control in the sliding mode. So eventually we realized that such a control actually bring a lot of benefit. In particular, this is kind of we call high gain benefit. Here is one of the example. If I use the linear control, my steady state, if I have a sort of a bounded disturbance, right? The arrow will be bounded by this parameter. But if I use this control, you can see the only difference is 1/3, and the steady state is bounded by this arrow. So this is epsilon over lambda brackets 3. But if you imagine if it's 0.1, this is going to be 0.001, right? It's a much more accurate. So this is actually the high gain. So that's why you bring this non-smoothness, and the switching is another. you actually improve the system performance dramatically. Okay. Okay, just show you some of the example. I want to talk about some other things. Just give you this as an example, how to compare these two. We use two controller. One is the linear one, another one is the fractional power. So eventually, I'll just show you the diagram. Eventually, you can see that this is a linear control. This is a conventional, Lipschitz condition-based controller. You can do that, and this is the terminal. You can see the convergence is much faster than that one. Actually, if you enlarge this part, it's actually very quickly arriving there and stay there forever. So that's the benefit, of course. When you introduce non-smoothness, you also introduce complexity. So that's become a research topic for the last many years, and there are many research papers talking about it. Okay. So I'm just before I just want to leave some time for discussion. I just want to look at some of the future challenges. So, as I mentioned before, there's a gap, between the methodologies dealing with discontinuous controls, and there's a piecewise Lyapunov method. There's average theory, and there's critical theory. We mentioned already is there's something in between. So how do you analyze the system? They're not too fast, they're not too slow. How do you understand the system in design in between, which is become one there is a still, haven't been any unified theoretical framework in that sense. So I think there's a lot of work needs to be done. The second thing is that given that the time delay element is inevitable, in particular we use computer control, you digitize the control, you have a discrete sampling time, and that time become your switching, acting time. So, and how do you study the rich behavior? We mentioned already for that very simple switching control system, you have a very rich dynamic behavior, you have periodic behavior, you have all different periods. So that's actually referred to chaos theory, right? But the chaos theory is a study of the smooth system, right? But what we are dealing with is a kind of a piecewise, you can call it piecewise switching, piecewise maps, those type of new mathematical theory. And how do you understand? What does that mean? Does it mean chaos? Yeah, or not? We just don't know. Because in chaos they say that if for that kind of a smooth mapping, mathematical mapping functions, if you have a period 3, you basically could have every period. So that's what we call the chaos. But in this system, we just don't know whether that's still applicable or not. But of course, that's beyond our scope at present time, and hopefully somebody else can pick it up to give us a brand new theory. The second thing is that's mentioned before. This is also the gap between continuous time and digital control. You design all the controller beautifully, but when you implement it, you have to digitize it. So there's a gap. We mentioned that there's a gap. If you don't dealing with that gap carefully, when you digitize it, it gives you completely chaotic behavior. So don't be surprised. There's a but the question is, how do you understand the gap? To look at the stability, a continuous time control designed to stabilize system, and what happens when you digitize it. So basically, when you digitize it, you introduce another parameter variable, which is the sampling period. So the sensitivity of that digitization with the sampling period, the continuous time sampling period, is sometimes critical, in particular in this continuous system. And third point is multi-time scale. So all we have learned so far is that we only have one time scale, right? You have time, and you look at the differential equations, then you study it. But if you look at the practical system, in particular these days, large scale system. Let's look at smart grid or power network, power system, right? You have different level of time scale. You have millisecond level at the controller, the control, for example, the rotating machine, the generators, that's millisecond. And you have area control, means coordinate the network, a sub-network of generators That's probably minutes, and you have a planning control, which could be hours. So you basically have this kind of physical system enabled by the information technology devices, and at different level they have different control and different time scale, right? So how do you deal with that? There have been that's in the 1980s and 90s, there has been some research done on what they call the two-dimensional system. Two-dimensional is not a two-variable system. It's two-time scale, T1 and T2, which would give some kind of glimpse of what's happening in the system. But because it's very difficult to study, there are very few results in that. But if you look at what we are facing right now, this problem we are coming to us inevitably. How do we deal with that? So that's another problem needs to be paid attention. The last one is the chattering. Is when you're dealing with switching control, in particular sliding mode control type of thing. The chattering is a major problem, right? There's so many methods, and how to deal with that is become another challenge. So one thing I just want to say, just beyond just this continuous control is as I mentioned before, these days the industry system are networked, connected, so they form this kind of a large-scale network. So the original, the conventional centralized control. The control theory basically is a centralized control. You basically have a supervisor kind of a role, know the system and design. Human is one. Design this kind of a unified control. Basically, I need to know the information everywhere. I need the feedback, and I can impose this kind of centralized overall control. But if you look at the human society, we are individuals. We have intelligence, right? We don't need broadly, we don't need somebody telling us what to do for everything. Something, So you have this hierarchical system. They have their own intelligence. They have their own scope, and they're bounded by law and rules, and we act on it. As the intelligence entity, we act on it. So the whole system we act on is distributed. We distributedly exercise our own right. We bear the consequences, good or bad, and the whole society moves. So that's actually kind of a distributed system. So that's, I think, given the future energy power system, not power system, the physical system become larger and larger, so network, we have to impose this kind of a distributed system. Now the question is that when you have this kind of distributed system over a very large network with all different kind of components, and how do you deal with that? You can use conventional control theory, and there's lots of research already. But if I use this continuous control, as we discussed, there's more problem, right? I mean, when there's dealing with discontinuity, and also there's a problem with dealing with digitization of this continuous control. If you look at the network level, what's happening? So there's a completely very new sort of a field. The second part is actually how to simplify. I mean, the physical system in the future become larger and more complex, and you just cannot model precisely to get all the variables, and you might dealing with the millions of variables. You can't deal with that kind of system. We know that usually we're dealing with the physical system no more than third or fourth order. 10 or 20 order is already very high, but not to mention thousands and tens of thousands. How do you deal with that? You have to simplify. So there has to be a way of dealing with the simplification, because sometimes you do want to get solution quickly, but you don't want to get accurate solution. You want to get approximate solution, and how do you get it quickly? So there's a balance between the fast response and the complexity. How do you deal with that? How do you have to find a way to simplify it? More specifically is what are there are some emerging issues, as I already sort of touched on earlier on, this continuous control in complex network. For example, this is one of the examples. If I have this kind of a very complex network, and I have the connections is in and out, right? You can see that. you first you look at it, this may not be discontinuous control, but if you have this switch on and off, it is a discontinuous differential equation, right? Forget about control, but when the feedback control is imposed on system, you basically end up with the ordinary differential equation with right-hand side discontinuity. So the whole discontinuous theory can be equally applied to study this kind of a huge network which has this connection. You treat the connection as a control phenomenon, and what happened? You can use average theory, you can use OR theory. So there's one way. So another way is that if I have this very large control theory, how do I control this kind of such a large control theory? So one way you could do is that one way you can do is that what you do is you can use average method to do that. What happens is look at this example, right? If I switching between 1, 2, from 2 to 1, 1 to 3, 3 to 2. So one way is I study each of them individually and I see how them connect together. But if they are sort of a periodic switching fast enough, what I do is I pack them together, right? Put them together, average them, and I study this static network, and I got a solution. And I know that if they switching fast enough, this is a pretty good approximation. So this is just one application to use this method in the discontinuous concept. So another way you can do is that basically for the slowing switching, that's what you do is you can use this multiple diagonal function. You can construct a multiple diagonal function, and eventually you get to the constraint on the sampling period. Sampling period has to be no smaller than a particular threshold, so the whole system will apply. But also you can use sliding mode theory to study that as well. Another work we've been doing, but we haven't listed here, is basically is that instead of controlling the whole network, every node, whether we can find a set of sort of controlling of, for example, just a very few, 1 or 2 or 3, so I can using that a few to control the whole system, right? So that's usually call pin control. So that's is related to understanding the topology of the system and to see the topology relationship and the control relationship. Eventually, I design a few controllers to basically to control system. May not be control the whole of them, but I probably will be able to control a majority of them. But of course, there's a way how to measure that. So this is sort of another work we have been sort of doing at present time. I guess, let me see. I think I might just stop here. I think, hopefully, I've presented clearly what my sort of experience and understanding of the issues in the discontinuous control, and hopefully they are going to be helpful for your future research. So thank you.
Okay, thank you very much. So now we have 10 minutes for questions. Do we have any comment and question?
Sorry, I couldn't hear clearly.
Okay.
Okay, thank you for your interesting talk. For a beginner in switch time system like me, I find the talk is very interesting. So I have a small question. I'm interested in design an observer for the system, but a little bit more general system. I mean, descriptor system and sometimes time delay system. So, how to prove the Zeno behavior could not happen, because I rarely found research to do that. Usually, it is previously assumed that it could not happen, but no clear proof.
I think if you design observer,
Sorry, I can.
if you design that and you have a sort of a theory, give you guaranteed convergence, then you wouldn't have zero behavior because you deliberately designed that. So this shouldn't happen. Then you wouldn't have zero behavior because you deliberately designed that. This shouldn't happen. Then you wouldn't have zero behavior because you deliberately designed that.
So anh Văn Bích
I'm very sorry because maybe the network has some problem. But I have another question. When we study about discontinuous control, of course it's more difficult than the continuous control. So what about the main difficulty when you study about discontinuous control?
I think the main challenge is when you have discontinuous control. Basically, as I mentioned in the slide, some part you have differential equations, and you have right hand side is discontinuous. You know they have different value on different conditions. So that imposes the difficulty. Difficulty, of course, as I mentioned before, if you're not switching fast enough. For example, if I have two options on the right hand side, I can solve each of them individually. But the problem is that the speed of switching between these two. As I mentioned before, there's a theory that you cannot switch fast enough so that if I design the two systems, they are stable, and I can imply that the overall system under this two value switching still asymptotic stable. Right? But then deriving that condition is difficult because I mean solving the differential equations of smoothly is not that easy already. But when you design it kind of switching, it becomes difficult. It's very much, and also that condition very much related to the structure of the dynamics. For example, if the linear system is actually related to the argument structures of each linear system. So I think that's the extra challenge, I think.
Okay, thank you very much for the presentation. Do you have any comment, question? Okay, thank you, Professor Zhu, again for the presentation.
Thank you very much. Nice to see you, all of you, and hope hopefully to see you next time. Okay, bye-bye.
Thank you, Steve.
Thank you very much. Thank you.